And once the class is over within the 40 minutes, you need not re-enter the class. Just the 40 minutes listening is sufficient, because the whole day you have to be there for the practical classes. Now you look at this. The last class we have seen the conjugate acid base equations. So this is what we discussed in the last class. If you take the sulfuric acid, when it loses one proton and HSO4 minus is formed, if you look in the reverse order, HSO4 minus is a proton acceptor, and it accepts the proton and becomes H2SO4. Therefore, HSO4 minus is a conjugate base. And I have also told you that Cl minus is the conjugate base of HCl, and H2PO4 minus is the conjugate base of H3PO4, the phosphoric acid. And also I have discussed the amphoteric nature of substances. Water molecule can act as an acid, and at the same time it can act as a base. Therefore, any substance which can act as acid and the base are called amphoteric. Similarly, ammonia can also act as an amphoteric substance. Now look here, I have already discussed why certain acids are called strong and why certain acids are called weak. And also we have derived the equation, Anderson-Hasselbalch equation, which states that the pH of a buffer is equal to the pKa value of the acid plus the log of salt concentration by acid concentration. Today we are going to see what is a buffer. Buffer is a mixture of an acid, a weak acid, and its salt. If you take a weak acid or a weak base and mix it with the salt of the weak acid or a base, then it is called a buffer. So I have given a few buffers. Lactic acid plus a sodium lactate is a buffer. Acetic acid plus sodium acetate is a buffer. Citric acid plus potassium citrate is a buffer. Phthalic acid plus potassium phthalate is a buffer. Similarly, ammonium hydroxide plus ammonium chloride is a buffer. So a weak base with its salt or a weak acid with its salt, they are called buffers. What are buffers qualitatively? Buffers are the substances which will try to maintain the pH for the addition of small quantities of acids or bases. Suppose if you have a buffer solution, and to the buffer solution you are adding a small quantity of an acid, immediately its pH won't change. The buffer will shift its equilibrium and it will synthesize more acid or more salt, and it will adjust in such a way that the change in the pH is minimized. Therefore, the pH of the solution will not change abruptly for the addition of a small quantity of acid or a base. So that is called the buffer solution. So the actual concentration of salt and acid, these are all the factors which affect the buffer capacity. The actual concentration of salt and acid, and also the salt to acid concentration ratio. These are all the two factors which affect the buffer capacity. Actually, the buffer is of a high importance in biochemistry. See, our mouth, our saliva is alkaline. Our stomach is highly acidic. Our intestine is again alkaline. Our blood is slightly alkaline. You look, the pH of the blood, it varies between 7.3 to 7.5. but actually pH of a blood does not show much variation. If the pH goes below 7, if the blood becomes acidic, or if the pH goes more than 7.9, the effect will be fatal. It is very dangerous. It is fatal to adjust the pH of the blood. So this is what is of very big importance, very big concern when people are admitted in the hospital for dialysis. While they are doing the dialysis or while they are treating the people, they should take care that the pH of the blood doesn't change. And also the osmotic pressure of the blood. So various factors which are working in our body. See, our mouth is always maintained alkaline because of buffer action. And also our stomach is maintained acidic because of buffer action. So whole body, there is a buffering. So buffering is working in all over the body. See, our brain, slightly alkaline. And also slightly alkaline brain is of a high intelligence quotient. Acidic brain, the intelligence quotient is very low. So the brain pH is also slightly fluctuating, but it is not varying much. It is sometimes slightly alkaline, sometimes slightly acidic. There is no big variation. The range is actually very small, but there is a buffering. Therefore, the buffer is of very high importance in the biochemistry. So now we are going to do a small calculation. I think if you are able to take down the problems which I have done, then it will be easy for you to understand the importance of the buffer. Look at this problem. Look at the first problem. First problem, I'm taking 3 different buffers. Look, first I take a buffer in which 10 ml of 0.1 molar lactic acid and 10 ml of 0.1 molar sodium lactate are mixed together. Suppose you are taking a test tube or a beaker in which you take 10 ml of 0.1 molar lactic acid and 10 ml of 0.1 molar sodium lactate. You mix them together. The pKa value for lactic acid is 3.86. So according to Anderson-Hasselbalch equation, the pH of the buffer is 3.86 plus log salt concentration by acid concentration. Actually, both you have taken as a 10 ml, 10 ml. Therefore, 0.1 divided by 0.1 into 10, which is not shown here. So this is the concentration. Equal volume is taken. So log 0.1 by 0.1 will become log 1, which is 0. Therefore, the pH of the buffer is 3.86. Now, I am adding 1 ml of 0.1 molar hydrochloric acid. Now, what will happen? This 1 ml of 0.1 molar hydrochloric acid will react with the buffer. The hydrochloric acid will not react with the lactic acid, but hydrochloric acid will react with the sodium lactate, and the sodium in the sodium lactate will combine with the chlorine and it will become sodium chloride, and the H plus here will combine with the sodium lactate, the lactate ion, and more lactic acid molecules will be generated. So how much of lactic acid will be generated? Now the 10 ml lactic acid will now become 11 ml lactic acid, because this 1 ml of 0.1 molar hydrochloric acid will produce 11 ml lactic acid, and it will consume 1 ml of sodium lactate. Therefore, the new volume of sodium lactate and lactic acid will be 9 ml sodium lactate and 11 ml lactic acid. So they are of equal strength, therefore you need not worry about the substitution of the strength. Simply the volume ratio is sufficient. because even if you multiply this by 0.1 and divide it by 0.1, it's all the same. Therefore, the new ratio is 9 by 11. Previously, that was 10 by 10. 10 ml divided by 10 ml. Now, when you add 1 ml of a 0.1 molar HCl, that 0.1 molar HCl will react with the sodium lactate, generating 1 more ml of lactic acid of a 0.1 molar strength by consuming 1 ml of sodium lactate of a 0.1 molar strength. Therefore, what happens in the buffer solution, after the addition of 1 ml of 0.1 molar HCl solution, you will be having 9 ml of sodium lactate and 11 ml of lactic acid. Therefore, if you do the calculation, that is, you are again calculating the concentration of, the pH of the buffer solution using Anderson-Hasselbalch equation. Now the pH is equal to 3.86 plus log 9 by 11. So you are getting 3.77. So the pH is not much varied. See, when a base is added, more amount, suppose to the same system, I am adding sodium hydroxide, what will happen? More amount of lactic acid will react with the sodium hydroxide, and more amount of sodium lactate will be generated. Therefore, lactic acid quantity will come down, sodium lactate quantity will go up. Therefore, this will become some 11 by 9. Now you are adding hydrochloric acid. So the hydrochloric acid will react with the sodium lactate, generating lactic acid and consuming sodium lactate. Therefore, the volume of the salt decreases, the volume of the acid increases. Therefore, even for the small addition of acid or base, the buffer will not change its pH abruptly. That is the concept. Therefore, on the addition of 1 ml of 0.1 molar hydrochloric acid to the buffer, I am getting the pH of the new buffer after the addition. It is 3.77. Therefore, the change in the pH is equal to 0.09 units. Now I am going to the second situation. I am diluting the buffer. Look here. I am taking 10 ml of 0.025 molar lactic acid and also 10 ml 0.025 molar sodium lactate. Suppose if you calculate the pH of this buffer, that is a 10 ml 0.025 molar lactic acid and 10 ml 0.025 molar sodium lactate, now the pH is equal to 3.86 plus log 0.025 divided by 0.025. It is also 3.86. The pH of the buffer is not changed due to dilution, because you have diluted the acid and diluted the salt to the same extent. Suppose if you differ the dilution or if you differ in the volume, then the pH will be different from the pKa value. As long as the volume and the concentration of the acid and its salt are the same, then the pH is equal to pKa. So now the pH of this buffer is equal to 3.86. Now you add 0.1 molar HCl of 1 ml volume. So now I am adding 1 ml of 0.1 molar hydrochloric acid to the buffer. Now what happens? 1 ml of 0.1 molar hydrochloric acid is equivalent to 4 ml of 0.025 molar sodium lactate. So you should understand this point very carefully. When you add 1 ml of 0.1 molar, see, this is stronger than the actual sodium lactate present in the buffer. The sodium lactate concentration is 0.025 molar. I am adding 0.1 molar. Therefore, this is 4 times stronger. What will happen? This 1 mole, this 1 ml will consume 4 ml of sodium lactate and 4 ml of lactic acid will be generated. Therefore, now the pH of the solution after the addition of 1 ml of 0.1 molar hydrochloric acid becomes 3.86 plus log of 6 ml of acid divided by 14 ml of the salt. 6 ml of salt divided by 14 ml of the acid. So the pH will be 3.49. Now look at the difference. The change in the pH is 3.86 minus 3.49. it is 0.37 units. Therefore, in previous case, there was only a very small change, 0.09 pH units. But in the new case, it is 0.37, several fold higher than this. Several fold higher than this. Now I am doing another calculation, the third case study. What I am doing, I am taking the lactate buffer, but now I am taking 50 ml of 0.1 molar sodium lactate and 5 ml of 0.1 molar lactic acid. Now I am going to calculate the pH of the buffer. It is pH is equal to 3.86 plus log 15 by 5. So this is equal to 4.34. So 4.34 is the original pH value of the buffer that we have synthesis, that we have made by adding 15 ml of 0.1 molar sodium lactate to 5 ml of 0.1 molar lactic acid. Now to this buffer, I am adding 1 ml of 0.1 molar HCl solution. What will happen? This 1 ml of 0.1 molar hydrochloric acid will consume 1 ml of sodium lactate and it will generate 1 ml of lactic acid. Therefore, the new ratio will be 14 by 16. So look here, after the addition of 1 ml of 0.1 molar hydrochloric acid, the pH of the buffer will now be 3.86 plus log 14 by 16. See, previously it was 15 by 5. Now it is 14 by 6. Why 14 by 6? That added 1 ml of 0.1 molar of HCl has consumed 1 ml of sodium lactate and it has added 1 ml in the acid solution. All right. So sorry, it has consumed 1 ml from the sodium lactate here and added 1 ml to the acid solution. Therefore, the sodium lactate quantity now it has become 14 ml and the acid quantity now it has become 6 ml. Therefore, the new pH will be, that is the pH of the buffer after the addition of 0.1 molar 1 ml hydrochloric acid is 4.23. Now, what is the change in the pH? So change in the pH is now 4.34 minus 4.23, you are getting 0.11 pH units. Now you compare these values. In the first case, it is 0.09 pH units. In the second case, it is 0.37 pH units. And in the third case, it is 0.11 pH units. Therefore, the least one among the three is 0.09 pH units. Therefore, if you want to construct, if you want to make a very good buffer, you should take buffer with acid and the salt of high concentration. Look here, here also it is a high concentration, here it is a low concentration. So when you took the acid and the salt with low concentrations, the change was much. When it was taken at a higher concentration, the change was less. And when you are taking a buffer, you should take equal ratio, because when you took equal ratio, the change was the least. But when you take a different ratio, then the change was a big number. Therefore, in order to make a very good buffer, you should take the acid and its salt at a higher concentration, and at the same time, you should take the ratio unity. The ratio should be equal. The quantity and the concentration of the weak acid taken and the quantity and the concentration of the salt of the acid taken, if they are equal and higher, then the buffering capacity will be high. So this is what we understand from these three problems. Now, the last slide, I suppose. So this is, look here. Normally, the normal range of buffers will be 2 pH units on either sides of the pKa value. See, for the lactic acid and sodium lactate, it is 3.86 the pKa value. Therefore, one on the left and one on the right. Therefore, it can buffer from 2.86 to 4.86. Similarly, phthalic acid and potassium phthalate, it can buffer from 3 to 4 pH. Acetic acid and sodium acetate can buffer from 4 to 6 pH. Similarly, monosodium dihydrogen phosphoric acid and disodium salt of phosphoric acid, they can buffer between 6 and 8 pH. So whatever the pH range that we need, and we can choose a buffer accordingly. See, suppose sometimes we used to suffer from urinary infection. Actually, the urine is supposed to be slightly acidic. If the pH of the urine changes, that will cause more problems. In such cases, normally we are given this monosodium citrate or some citric acid, citralcohol, citric acid and potassium citrate buffers. Actually, you are given a syrup and which has to be diluted in water and it has to be drunk. Actually, what is it? It is a buffer. Citralcohol, citric acid and potassium citrate or sodium citrate, it is a buffer. Normally, if citric acid is present in a lemon water, you drink lemon water with the sodium chloride, that itself is a buffer which will try to maintain the pH of the urine. Similarly, sometimes what happens, your esophagus will get irritation due to the entry of the acid reflux from the stomach. Even then you are giving some base solutions, magnesium hydroxide or aluminum hydroxide, to neutralize the acid that is given. Therefore, even tablets are available to maintain the pH of our body. pH tablets are available. Therefore, the pH, the maintenance of the pH in various parts of our body with the use of the buffers are very important. But actually, the buffering is automatically taking place in our body by adjusting the acid and its salt combinations. The buffering is already going on in our body, but we can make the buffer tablets for us also. So these are all the importances of the buffering. If you have any doubt, you can ask me. Anybody has doubt? Anybody has any doubts?